Electronegativity and polarity. And this is really why we have to talk about electron shapes. You probably are all aware that if you combine oil and water in a container, you can't get them to mix, can you? We sometimes make Italian salad dressing with the good seasons, mixes in the little cruet, right? And you add the oil and the vinegar and the water, and the oil always sits on top. You can close the lid and you can shake it all day long, and as soon as you set it down, the oil starts to come up to the top and it separates. The reason is chemical. There is something about those water molecules that causes them to clump together and exclude the oil. So it's a little bit, going back to high school again, there were those cliques, right? And there's this group of people, and you just can't get into that social circle. They will sometimes literally just push you out. They'll elbow you out if you try to get into their circle. So we're going to look at why that is with water and oil. So here's a Lewis structure for water. The oxygen and the hydrogen atoms are each donating one electron to the covalent bond that's between them. So this bond here, remember we sometimes drew it with dots at each end because it's two electrons that are being shared. Those electrons are being shared, but they're not shared equally. It's a little bit like, the 7-year-old shares a cookie with the 2-year-old, and he breaks it in half, and it's not really in half, right? But you give the little piece to the little kid, right? Because he doesn't know any better. Here, in this hydrogen-oxygen bond, they're sharing the two electrons, but oxygen is getting more of it than its fair share, and hydrogen is getting left out. The reason is that oxygen is more electronegative. Oxygen is more attractive to electrons. So it hogs the electrons that are being shared with hydrogen. So electronegativity can be defined as the ability of an element to attract electrons within a covalent bond. Electronegativity can be measured. It uses a relative scale. Fluorine is the most electronegative element. It was assigned an electronegativity of 4, which is kind of like a grade point average, it's 4.0. And then they just rank everything below that. So if we look at this hydrogen-oxygen bond and we look at a multiple exposure photograph of where the electrons are, this is what we're going to see. We're going to see that there's more electron density around the oxygen than around the hydrogen. The electrons spend more time over here because oxygen's more attractive. So let's go to crazy analogy. So here we have oxygen. This is a home where a little boy, an electron, lives, and next door is the hydrogen house where another little boy, electron, lives. And these two little boys are going to play together. So they're out playing, and over at hydrogen's house they have an old CRT television. They don't have cable or anything, they've just got some Barney videos and maybe a couple Thomas the Tank Engine videos. And if you're hungry, Mom will give you saltine crackers and a glass of water. They don't even have an ice maker, so it's just like straight out of the tap. And then over here at Oxygen's house, they have a big screen TV. They've got every latest game system. They've got cable television. They actually have a soda fountain in their kitchen. What? And if you're hungry, the mom will order pizza to be delivered, just like that. Where are those two little boys going to play more? Outdoors. Outdoors, but closer to Oxygen's house, right? Right? Why? It's more exciting. It's more attractive, right? So that's the same thing with the electrons. Oxygen is more attractive. It has a greater pull on the electrons than hydrogen does. The electrons are shared. Those little boys do go over to hydrogen's house sometimes. you got to change your underwear sometimes, right? Or just, give your mom a kiss or brush your teeth or something, but then they're going to go back over here. It's not that the oxygens have adopted little hydrogen boy, right? He still is from the hydrogen family, but the little boys are sharing between the two houses. The electrons are shared. So we have this uneven sharing, and that results in an uneven distribution of charge. So if the electrons spend more time over here, then this end of this bond becomes slightly negative. It's not a full -1 charge. That would happen if the electron was transferred from the hydrogen to the oxygen, then the oxygen would have a -1 charge. So it's less than a full charge. And over here, the hydrogen is going to have a slightly positive charge because it has its 1 proton, but it doesn't have an electron around it all the time. The electron's, kind of going over here a lot. Does that make sense? So this bond then has ends that are different. On our planet, we have a north pole and a south pole. They are different magnetically. So polar has to do with two ends of something that are different. So we say this is a polar bond. We say it has a dipole moment. That always makes me think of senior moment. But anyway, it's just a dipole moment. Dipole meaning two poles. So we have a partial negative charge here, partial positive charge here. So these letters, when we run out of the English letters, because we've used them for too many things, then we start using the Greek letters. This is the lowercase Greek delta. So it's a D. It kind of looks like a D with really bad posture. It's all curvy and bent over. So this is partial negative, that's partial positive. There's a separation of charge. So this is a covalent bond. It's a sharing of electrons, but the electrons are not shared equally. So we say it's a polar covalent bond because it's lopsided. The bigger the difference in electronegativity between the two atoms, the more polar the molecule is. What I described to you with the little kids, that's pretty extreme difference between two houses in the same neighborhood, right? Usually the difference is going to be much less. And so then the sharing will be more equal.
Redistribute the wealth.
Redistribute the wealth. Yeah, but if everybody's the same, that's no fun. So here's a graph showing the electronegativity differences. So here we have fluorine. Fluorine has an electronegativity of 4.0. Fluorine is the coolest house for little boys to go to. They also have a swimming pool and a trampoline in the backyard. I mean, it's just an awesome place. So everybody wants to go over here to fluorine's house. Oxygen's pretty cool, but fluorine's better. And we see here there's sort of a trend that generally, as you move away from fluorine, the elements become less and less electronegative. Okay, so there are different elements that do have the same electronegativities, like carbon and sulfur have the same electronegativity. But generally, if you look at any two different elements, they're going to have different electronegativities. Why aren't the noble gases on there? They don't like to interact with anybody at all. They don't really form covalent bonds. Some of them do, but not very often. So there's no point in even talking about how they attract electrons. In fact, for helium, which no known compounds form, there's no way to figure out how attractive it would be. So we just leave those out of there. There may be some homework questions that ask you very specific things that you might need to look at this table for. We're not going to use a table like this on any exam questions. I do want you to see that the trend is, as you go across the periodic table, the electronegativity increases. As you go down, it decreases. Basically, the farther you are from fluorine, the less electronegative. If we have two elements in a covalent bond that have the same electronegativity, So two little boys' houses, and they've got the same fun stuff for little kids. The kids are going to spend an equal time at each house. It's not even that one mom is grumpier than the other. Everything is equal. They're going to spend equal time. So if the electronegativities are the same, then the electrons are shared equally, and there's no dipole moment. So this is called a nonpolar covalent bond, because there aren't poles. There's no difference. It's very symmetrical. So here we have a chlorine molecule, chlorine bonded to chlorine. Well, it's the same element. Obviously, the electronegativity has to be the same. This is a nonpolar covalent bond. The electrons are shared equally. Anytime you have two atoms of the same element, it's going to be a nonpolar bond. If we have a really big difference, then we actually get the electron being transferred, and then the bond is ionic. And I suppose, analogies always get a little twisted when you take them too far. But this might be where it wasn't just that hydrogen's home, they didn't have a lot of stuff, but maybe like the parents had taken off, or the parents were abusive or something, or the house burned down and the parents were killed. Anyway, the electron actually got adopted by the neighbors, got transferred. So an ionic bond, the electronegativity difference is so big that the one atom actually takes the electron from the other. So in sodium chloride, there's no sharing going on. Chlorine took the electron, and sodium let chlorine do that. But now, because of the opposite charges on those two ions, they're very attracted to each other. Kind of ironic if you think too far about it. If we have an intermediate electronegativity difference, then we have a polar covalent bond. So hydrogen and fluorine. Fluorine's more electronegative, so it has a partial negative charge on this end of the molecule because it hogs the electrons. The electrons want to go over here because it's nicer for them. They're attracted to that. And hydrogen's over here with a partial positive charge. It's very common to have polar covalent compounds between two nonmetals. If you have a metal and a nonmetal, that's going to be an ionic bond, because metals aren't good at sharing. It's like either I'm going to keep my electrons or I'm going to give them to you. You can have them, but I'm not going to share. So there's a continuum between no electronegativity difference, or the largest electronegativity difference possible, which is 3.3. And so here's pure or nonpolar covalent bonds on this end and ionic bonds on that end, polar covalent in the middle. We need some lines. We just kind of have to draw some lines. And so I'm not going to quiz you or test you on where those lines are drawn, but the guidelines are if the difference is 0.4 or less, that's considered a nonpolar bond. If the difference is 0.4, there is a little unevenness of sharing, but it's just not enough to make a difference. If the difference in electronegativity is from 0.4 to 2, that's considered a polar covalent bond. Differences greater than 2 are considered ionic bonds. And so that kind of summarizes up here. So what should you be able to regurgitate or spit back for me? See, do I have it summarized? No, I don't. I should probably add a slide here, but yeesh. Nonpolar. Well, actually, let's do it this way. So here we have, they say pure covalent. I think that's silly. Nonpolar covalent bond. So if you have two atoms of the same element, it's going to be nonpolar. It's also possible that you can have two different ones, like carbon and sulfur or carbon and hydrogen. I don't expect you to know that. But if you see two atoms, the same element, you should know that's a nonpolar bond. Ionic bonds, you should identify that if you have a metal with a nonmetal. So like in that example, NaCl, sodium's a metal, chlorine's a nonmetal, that's an ionic bond. It's an extreme electronegativity difference. And then the middle one, the polar bond, that would be two different nonmetals. So you've got two different nonmetals. And this is not a hard and fast rule, but it's going to be right most of the time, and that's going to be just good enough. So two nonmetals, different ones, okay? So if we had like a phosphorus bromine bond, those are both nonmetals, and they're not the same element, so I would expect you to predict that that's a polar bond. If we have nitrogen bonded to nitrogen, what would that be? Nonpolar. How about copper bonded to nitrogen? Ionic, because copper's a metal. Okay, so let's do some examples here. Is the bond formed between each pair of atoms pure covalent, polar covalent, or ionic? I'm going to change this again to nonpolar. So between iodine and iodine, that's going to be nonpolar. How about cesium and bromine? Ionic. And you really just need a periodic table all the time, don't you? How about phosphorus and oxygen? Polar. Two nonmetals. They're both nonmetals. They're on the right of that stair-step line, so it's going to be a covalent bond. They're different, so I would expect you to tell me that they are polar. It's a polar bond. Any questions? So we had to learn about polar bonds so that we can talk about polar molecules. You can have polar bonds in a molecule, but that doesn't necessarily mean that the entire molecule is polar. A polar molecule will have one end that is more negative and one end that is a little more positive than the other. So a polar molecule is going to have a net dipole moment. Strictly speaking, what we're talking about here is we're taking those bonds, the dipole moments in the bonds, and we're adding them together. If you're into math, this is adding vectors in three-dimensional space. Anybody like that kind of stuff? Yeah, I didn't think so. If you have a diatomic molecule, diatomic means two atoms, right? So like hydrogen chloride, one hydrogen atom bonded to one chlorine atom. Well, then you can just look and see, well, if the bond is polar, then the molecule's polar. If you have more than one bond, though, we have to look at the shape of the molecule before we can tell if the entire molecule is polar or not. So we'll start with one that's relatively easy to understand. So here's carbon dioxide. We looked at this one earlier and we decided it was linear because it has these two electron groups, right? If we look at this bond between oxygen and carbon, is that going to be polar or nonpolar? Are carbon and oxygen nonmetals? Yeah. Are they different nonmetals? Yeah. So this is a polar bond. So another way that we can represent polar bonds is with an arrow that has a plus on one side. And so in the little kid analogy, this is like dad coming home and say, "Where's Junior?" And the neighbor says, "He's over there," pointing to the more electronegative one. Okay? So in this bond, oxygen is more attractive to the electrons, so it's pulling them this way. Over here we have another carbon-oxygen bond. And this oxygen is pulling the electrons that way. It's kind of like they're playing tug of war, right? Each of these bonds has the same amount of polarity, the same size dipole moment, because they're between carbon and between carbon and oxygen. The difference in electronegativity between carbon and oxygen is the same as the difference in electronegativity between carbon and oxygen, right? Well, duh. So it's a little bit like playing tug-of-war. So here's the center of the rope, and we've got one strong guy pulling on this side and an equally strong guy on the other side pulling exactly the opposite. What's going to happen? The guys are going to get tired. Is the center point of this rope going to move if the people on each end are equally strong? No, it's just going to stay there. So these dipole moments of the individual bonds cancel each other out. We're taking a vector in this direction and adding it to a vector in exactly the opposite direction. The vectors have equal magnitude. They cancel out. It's like adding 5 and negative 5. 5 plus negative 5 equals 0. So this is a nonpolar molecule. It doesn't have a positive end and a negative end. It's just all the same. Any questions? Let's look at another one. Or maybe not. Oh, we'll look at water in a minute. So we can represent those polar bonds with arrows that point in the direction of the negative pole and have a plus sign in the positive. If the arrows are going in exactly opposite directions, then those dipole moments are going to cancel. So here's water. So water has this bent shape because of the two lone pairs on it. But here we're looking at the molecular shape. So here's the shape of the molecule. Oxygen is more electronegative, and so this dipole moment is going towards the oxygen. The oxygen gets more of the electron density than the hydrogen does. And then over here, the same thing is happening. The oxygen is hogging the electrons that are being shared with hydrogen. So this would be a situation if you're playing tug-of-war, where there you've got the flag, and you've got one guy pulling this way and one guy pulling that way. Is that rope going to move? Yeah. The rope is going to move down this way because all the forces are on this side of it. Nothing's opposing it on the other side. Water is polar. It has a dipole moment. So if we take an arrow like this and add it to an arrow like that, the overall result is, I made that a little too long, but you get the idea. The blue line is the overall result of adding those two things together. So the oxygen end, sorry, this is the oxygen end. The oxygen end of the water molecule is a little bit negative, and the hydrogen end is a little bit positive. Water's a polar molecule. So you need to be able to predict whether simple molecules are polar or nonpolar. There's different ways to do that. One way is, by understanding a table like this. So here, if you have two identical polar bonds in opposite directions, it's going to be nonpolar. If you have three identical polar bonds in opposite directions, it's also going to be nonpolar. If you have three polar bonds with a trigonal pyramid, it's polar. Polar bonds and a bent molecule,
So is it only
polar.
when it has an electron pair?
Pardon me?
Is it only polar when it has an electron pair?
We're getting to that. Is it only polar if it has an electron pair? Almost. And then here, if you have four identical bonds on the tetrahedral. So the tetrahedral, the nonpolar, the linear and the trigonal planar are often going to be nonpolar. So to figure out whether a molecule is polar, first of all, you have to identify, does it have polar bonds? If all the bonds are nonpolar, it can't possibly be polar. So if you have two bonding atoms that have different electronegativities, you've got polar bonds. Then you have to figure out if those polar bonds add together. You need to look at the Vesper theory shape and then ask yourself, is the molecule symmetrical? Most 3A students don't enjoy doing all of that. So here's my alternate method. This is what I would recommend. Look at the Lewis structure for the molecule. It's nonpolar if both of these are true. There are no lone pairs on the central atom, and the atoms that are bonded to the central atom are all the same, or they have the same electronegativity. On test questions, they'll all be the same. So let's use my alternate method to figure these out. Determine whether CH4 is polar. Well, first we need the Lewis structure. So the Lewis structure for this, not going to spend a lot of time on it, is like that. There's no lone pairs on anything. So to identify whether this is polar or not, we first ask ourselves, are there any lone pairs on the central atom? No. So the first condition is true, no lone pairs. Are all of the atoms that are bonded to the central atom the same? Yes. Therefore, this is a nonpolar molecule. It's nonpolar because it's symmetrical. It's a tetrahedron, and if you add all those vectors up, they add up to 0 because it's symmetrical. Let's do NH3. So this would have nitrogen in the middle and 3 hydrogens and a lone pair on the nitrogen. There's the Lewis structure. So then we ask ourselves, are there any lone pairs on the central atom? Yes. So condition number 1, no lone pairs on the central atom, is not true. We don't have to go any farther. This is a polar molecule. So it really does have to do with those lone pairs on the central atom. Does that make sense? Because what happens, if we looked at the shape of this, the electron geometry is tetrahedral. But one of those points is a lone pair. And then when we take these 3 polar bonds and add them together, there's nothing up here that's pulling to oppose them. And so the vectors are not going to add up to 0, and it's a polar molecule. SO2. You might be tempted to just guess on this one and say, oh, that's nonpolar. It's like CO2, right? You have to get the Lewis structure first. So when we do the Lewis structure, what happens? So we have 18 valence electrons, 6 from each of these. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So I need to make a double bond. I'll take an electron from the sulfur and put it in here. And now I've got octets. This is going to have resonance, but we don't need to think about that for answering this question. So there's the Lewis structure. Is it polar or nonpolar? Polar. It's polar, because there's a lone pair in the central atom. So what's the molecular shape? The electron geometry is trigonal planar, because there's 3 electron groups. Bent. Because one of those corners is a lone pair. So we've got, if that's the double bond to the oxygen, and here's the other oxygen. There's a lone pair up here, but he's invisible. So then if we look at the, here's the sulfur in the middle. So the oxygen's more electronegative. So we've got a dipole going this way and a dipole going that way. And those don't oppose each other directly. Yes?
We draw the lone pairs in the homework. I'm not doing a question like this, but if there is, will we draw the lone pair up top?
If it's asking you to draw a Lewis structure, you have to draw the lone pair. If you're just looking at shapes, I don't think it's actually going to ask you to draw anything like that. So this is a polar molecule. Any questions? So now we can talk about why oil and water don't mix. Water molecules are polar. Oil molecules are nonpolar. So two water molecules are attracted to each other because the hydrogen end is a little bit positive and the oxygen end is a little bit negative, and so just like opposite poles of magnets, they attract each other. So this water molecule is electrostatically attracted to the neighboring water molecule. We don't have electrostatic attractions like that between the oil molecules. So these guys are more attracted to each other. They tend to clump together and form a clique and push the oil out because the oil cannot interact with them in that same way. So when we have a mixture of polar molecules and nonpolar molecules, they're going to tend to separate. Just like if you had a bunch of regular glass marbles and a bunch of magnetic marbles. The magnetic marbles here are the solid colored ones. They're attracted to each other. They stick together. They go click, 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 and they all bunch up, right? The regular glass marbles are just like, yeah, what's going on? They're just rolling all over the place. And you can try all kinds of different things mixing these up, but the magnetic marbles are always going to clump together. And that's what happens when we mix oil and water. The water is clumping together. It's very attracted to the other water molecules, and it pushes out the oil. The reason the oil goes to the top of the beaker instead of the bottom is because it's less dense than the water. There are other nonpolar substances that are more dense than water, and then they get pushed to the bottom, and water's on top, and something like methylene chloride is going to be on the bottom. Any questions? So here's something practical. How does soap work? Has to do with this idea of polar and nonpolar molecules. So Thanksgiving's coming up, and I always bake pies, and you have to use Crisco, right? And you get it on your hands, and then you just can't get it off, right? You can go rinse your hands underwater and get sugar or flour or eggs off, but the Crisco will not rinse off with water, right? You can get a bunch of it off with a paper towel, but you've still got this oily, greasy stuff on your hand. How do you get it off? Soap. You got to use soap for that. There's no other way around it. Why does soap work? Because soap has a polar end and a nonpolar end. So here's an illustration of a soap molecule. So we have this polar end. This is polar. It interacts. It looks like a caterpillar, doesn't it? Eating a purple berry. The polar end is attracted to the water, and the nonpolar end is attracted to the grease. And so one end gets in with the grease, and one end gets in with the water, and it allows the grease and the water to mix together. Well, I thought there was another picture. There wasn't. I will make another picture. So what happens is you end up with little globs of the grease with the nonpolar tails of those soap molecules in there. It's a little bit like, circling the wagons or something. And then here you have those polar ends on the outside to interact with the water. You can think of it a little bit like language, right? So nonpolar things, maybe they're speaking Japanese, and the polar things speak Swedish. I'm picking on those two because I'm of Swedish descent and my husband is of Japanese descent, and so I can't be accused of anything. Not picking on anybody except people in my family. So if you have a bunch of people who only speak Swedish and a bunch of people who only speak Japanese, are they going to be able to mix and mingle very well? No, because they can't talk to each other. So they'll tend to clump up, and all the Swedes will be over here, and the Japanese will be over here, and they're just talking to each other, right? How do you get them to mix? You need an interpreter. You need someone who can speak both languages, right? That's what the soap does. The soap molecule can speak Swedish and Japanese. And so it facilitates the mixing of these things. So that's why soap works. See, my children